Hi, I'm Benjamin May,
And I'm Lilah Kelly.
and our presentation is over graphs and how the Skyscanner application uses graphs to sort and search for different flights and plane tickets.
So here's just a quick outline of what we'll be touching upon today. And the first thing is going to be graphs. So a background on graphs is that they're a data structure that show the connections between nodes and edges. Nodes are going to be where data is stored, and the edges are the links between the nodes. And that's going to be shown in an example right here. And as you can see, the nodes and the edges are labeled as such. As for types of graphs, we have undirected, which means that edges can go both directions, meaning that it can go between the two nodes either way. And a great example is a staircase where the two nodes are the first floor and the second floor, and you can either go up or down. There's really no intended direction for a staircase. But in terms of a directed, edges can only go in one direction. So a great example of this is an escalator, meaning, again, taking the second floor as node 1 and the first floor as node 2. If the escalator is going down, that is the only way or the only direction you can go. You can't go up because the elevator predetermines which direction you will be going in. So another type of graph is unweighted, which means the edges have no values. And then, of course, the counterpart is weighted graphs, which means the edges have values. And an example of this is trying to send a package to a friend, and the edge would be the length the package will travel between your house and your friend's house, which in this example is 36 miles.
So there are two primary ways to implement a graph data structure. And so one includes using an adjacency matrix, which is what we see in this picture here. The other way uses adjacency lists, which is essentially kind of a version of a linked list. And the implementation examples we will go over later on is going to use a adjacency list here. So the Skyscanner application, so this is a blurb from their website about them. So they started in 2003, and they really set out to do things a little bit differently than other like places you could buy tickets from or going through a travel agent. They wanted to have all flight options available for you in one easy, convenient location and allow you to search for flights based on your specific criteria. So what the Skyscanner model is, they essentially search all available routes worldwide, and they put them together, like I said, in one convenient location. So you can select the flights and tickets that kind of best fit what the user's specific needs are. So Skyscanner also allows you to book flights, hotels, and rental cars now as well. So the application, so it allows you to search, sort, and purchase all from your mobile device, which is extremely convenient for everybody. It allows you to sort through flights by different criteria. These criteria include price, duration, outbound takeoff time, inbound landing or outbound landing time, return takeoff time, and return landing time. So you can imagine that the most popular and common of these are the price and duration, and that's what this project will focus on. So popular Skyscanner sorting, like I mentioned in the previous slide. So we'd have price, duration. This is a screenshot from the actual phone application. So it shows different ways to sort it. So for a specific flight, New York to Los Angeles, if we search by the price, you can see we can get the cheapest one here for $271. This exact same flight, if we select duration and sort by that, you can see that it's $418, but the flight time, 6 hours and 5 hours, are quite a bit shorter than 10 hours and 9 hours. So it allows users to find what they're looking for. So Skyscanner's use of the graph data structure. So as Lilah explained, so graphs include vertices and or nodes. So in Skyscanner, each one of those is represented by an airport, the vertexes. The edges are the different flights and routes between airports are stored in the edges. So edges of the flight graph, they're directed in this case because that helps you know what the origin and destination airports are for a particular flight. So we know that this node is the origin and it has a directed line or directed edge to the destination node. So weighted edges sorting flights in Skyscanner. So with this, in addition to being a directed graph, Skyscanner uses weighted graphs as well, where they can weight the edges by either price or duration, which is how it allows you to sort on the application. So they do this by sorting through the different ways. So if the graph is weighted by price, for example, it'll help you find the cheapest ticket. If the graph is weighted by duration, it'll help you find the quickest or shortest trip, which is what we kind of saw in an earlier slide. So, but now with that being said, the question becomes, how do they use the graph data structure with this implementation to make this all work? So for example, what I mentioned, so if I'm going from airport A here, and I'm going to airport D, so it's $200, for example, to do this direct flight. It's not labeled here, but say from A to C, this was $70. So I could have one layover. A to C is $70, C to D is $30. So even though it's a longer trip with a layover, it's only $100, which is half the price of the direct flight. And that's kind of a basic example of how they would do something like that. So breadth first search and shortest path. So breadth first search, what is it? So what breadth first search is a search algorithm that uses a queue to explore the vertices layer by layer from the initial starting node. As it moves layer by layer, it'll go through each layer until it has reached all of the other nodes in the graph. So Dijkstra's shortest path algorithm. So what this is, it's a way for you to traverse a graph and find the shortest path from a starting node to a target node. So for example, if we're starting here at S, it's going to go through to 1, add it to the queue, 2, add it to the queue, 3, add it to the queue. As we all know, a queue works by doing the first in. So now we go to 1, we check the nodes connected to that. We go to 2, check the nodes connected to that. Go to 3, check the nodes connected to that. And we'll see at that point, that's when we find our target. So now our shortest path is from start to 3 to target. Even though there are other routes available, they can get you from start to 2 to 4 to 5 to target. We're doing shortest path. So cheapest flight via constrained shortest path. So what that does is if Skyscanner would use every single shortest path they can find. So say there's 10 short flights, they're $50 each. That'd be a $500 ticket, but maybe no one wants to have 10 different layovers. So what they do is they put constraints in, and what that does is they can constrain it by the maximum number of layovers. So what it'll do, it'll search for all possible flights and get the prices for those as long as they have 5 or less layovers. And that's a way to make the results, so the different tickets available, more reasonable for both them and the user, because most people aren't going to want to have 10 layovers on their flight. So now with these constraints in place, Skyscanner is ready to get you the output for the cheapest ticket prices. So this is going to be a very basic implementation that shows direct flights on a weighted graph, and it'll output the prices of these direct flights. So if we come in here, first, what we have in this first method is going to create the edges. And you can see the edges are weighted by price. It has price here. It has the source, the destination. Then we're going to put these edges and create a graph with these edges on it. And then, so once we've created the graph with the weighted edges, we can come down here and we could print the output of all the different possible nodes to other nodes. And well, this down here in the main method is where we add the edges with the starting location, destination, and the price. And then running this code here, which you can click on this link later on, or I've also included source code for it. This is what the output is. It's going to show all the different available direct flights with the price of each of those direct flights on it. Next, we have a very basic implementation of shortest path. So for this one, it's going to be a very similar setup. So first, we're going to create the graph with the total number of vertices that are going to be in the graph. We're going to add the edges to the graph. And these ones aren't weighted. So we're just going to add the edges. Then we're going to run the breadth first search to get the shortest path. It's going to traverse the entire graph. And it's going to look from the root node, which is going to be your starting destination. It's going to be looking for the target node. And when you run this code, what the output is, for example, if I'm starting from edge or vertex 0 and I'm trying to find vertex 5, the shortest path would be from 0 to 1 to 5. So 0 to 1, 1 to 5. If I just put in 1 and 5 are my two airports, I'm going to get from 1 to 5 as a direct flight, even though you can see that from 1 can go to 2, 2 to 4, 4 to 5. So there are other routes, but this is giving me the shortest path. So again, you can click on this and play around with it a little bit later.
So why did we choose graphs? A huge reason is because a lot of our prereqs didn't really cover this data structure. We covered primarily arrays and other linear ones. So this was really a chance for us to explore kind of an unfamiliar data structure. And another huge reason is that we're both out of state, which means a huge part of us getting to and from campus is using airline apps, which means this is a very personal graph for us. And then graphs are also covered in many job interviews for coding, so this is a very important one to have a strong background in. In terms of an alternative in this implementation of a data structure, we can also use a linked list. Background is there are chains of nodes with pointers between them. Nodes are where the data is stored, and the pointers point to the next node in the chain. And the initial pointer is called the head pointer, and the end pointer points to the null. And if you look at this and you're seeing this, you're probably thinking, this seems very familiar to the graphs we went over in the beginning. However, this is sort of a way of explaining that it's not necessarily the same as a graph. And we're using the same example Ben used above, where we are using JFK to LAX and the different layovers and possibilities of that flight. But each individual linked list shows each individual flight path. So as you can see, it gets very hectic very quickly. So why aren't linked lists used? As we touched on before, there's too much memory. So each node contains its pointer to another node. That requires so much memory. And as we saw above, every single flight path requires its own linked list, which means there's like an insane amount of memory that needs to get contained, whereas a graph will contain every possible flight path in its one graph.
So another alternative we looked into was the tree data structure. So a tree is very similar to a graph. The main difference is that it's hierarchical. So you're gonna start from one single start node, and then you're gonna go down through that, and there's no like connecting to other layers. It just goes down layer by layer. So like with a graph, it also includes vertices or nodes to store the data. It has the edges, which can also be directed and weighted for a price. So here's a quick example. So say, again, if the nodes are airports, and then the number on the weighted edges are the price. So this would be a pretty decent way to do it. However, since again, we only have one starting node up here, each airport would have to have its own unique tree, and it couldn't, again, be all on one data structure in the graph. So that would be a downfall of it. So which, like I said, that's part of the reason it wouldn't be used. Each airport would require its own tree. Also, some of the nodes in the airport would be duplicates because again, since you can't go back and forth. So if our starting airport is JFK, everything comes off of this. So I go JFK to O'Dare in Chicago to Houston to LAX, or JFK to Chicago to LAX, or JFK to Miami to Houston to LAX. So you see there's a lot of repeating nodes where on a graph, we could just have a single LAX and there's gonna be a ton of edges pointing out to it to each of these different ones. So it makes it a lot more convenient and easy to use in one simple place. So for the discussion, what we learned in this is we achieved our goal. One of our motivations of learning more about graphs, we had a chance to look into it, learn about it on our own, and we really got a good, pretty decent initial grasp on it. And it's cool to understand how we did that, that it's made up of, the data structure is made up of, how to implement it, so on. We learned some of the search functions, like a simple breadth first search to traverse the graph, which is really neat to learn about. And then some of the coding implementations, just a quick look, but starting to get an idea of how they can actually be applied and implemented if we were to do it in the future. So the really cool thing about this is that, on each of our cell phones, I have pages of apps, I know, and I just usually take it for granted. But if you think about it, each one of these apps, you see the complexity that goes into it. And no matter how complex any of these apps are, if you break it down, most of them start with a simple data structure. And that's what we learned. And so this is the references that we use to complete this project. So again, I'm Benjamin May.
I'm Lilah. Thanks for listening.
Thanks for listening.